Today, I'm going to show you an area of maths called group theory. We will cover what a group is, some examples of groups, as well as some of the applications in maths and in other subjects too. It's my goal to give you an explanation of these concepts that is intuitive enough that you feel you could have discovered it yourself. Symmetry is all around us. We find it in nature everywhere. It's something that is very beautiful to us as humans. In maths, an object is said to have a symmetry if there is a transformation, such as translation, scaling, rotation or reflection, that maps the object onto itself. In simpler words, an object has a symmetry if you can move it and it still looks the same. For example, you could rotate a square 90 degrees and it would still be a square. So what exactly is group theory, which I mentioned in the beginning? Group theory is simply the mathematical formalization of symmetry. This happens to be a really useful thing to consider, and a topic that comes up time and again in maths and other subjects too. It started long ago with the great Swiss mathematician and polymath Leonhard Euler. Euler published a paper in approximately 1760 containing a proof of one of Fermat's theorems in which he referred to a very important group. It was one of the earliest contributions to group theory. A decade later, Joseph Louis Lagrange, Italian mathematician, physicist and astronomer, came up with a very important theorem about the size of groups. The Italian mathematician Paolo Ruffini then came up with another important theorem relating the size of groups and the size of their subgroups. The so-called Prince of Mathematicians Johann Carl Friedrich Gauss was the first to work with what are known as cyclic groups. Then, Niels Abel used group theory to prove the astonishing impossibility of solving the quintic, and Évariste Galois made incredible applications of group theory to algebra. Unfortunately, Galois died at the age of 20 in a duel where he was shot in the abdomen, but in his short life, he was able to develop one of the richest areas of maths, Galois theory, which researchers are still fascinated with today. In 1844, Augustin Louis Cauchy published the first work on the transformation of permutations, where he anticipated a theorem that wasn't discovered until years later. Finally, in 1854, nearly a century after Euler first discussed the concept of a group, Arthur Cayley has the credit for the first recorded attempt to give a definition of an abstract group. After all this discussion, it's probably about time we discuss what a group actually is. A group is defined by 4 axioms, but before we move on to this, we first need to discuss the notion of an axiom in mathematics. Axioms are simply the rules of mathematics. Without them, all of maths would fall apart, and no one would be able to agree on what is true and what is not. The axioms that maths is built on are called the Zermelo-Fraenkel axioms. There are 9 of them, which is too many for me to go through, but I will show you 2 of them so you have a clear idea of what an axiom is. The axiom of extensionality says that 2 sets are the same if they have the same elements. You can think of the sets as the coloured balls in these circles. Clearly, the sets are the same as they have 1 blue ball, 1 red ball and 1 green ball. There would be no way of distinguishing the 2. It may seem that this axiom is trivial, and it is to an extent. However, there is no way to prove it, so it must be stated explicitly so that we know what our assumptions are when we're doing maths. To give you an idea of how fundamental this concept is, there is no way to give a mathematical proof that 2 sets are the same if they have the same elements, but there is a mathematical proof to show that 1 plus 1 is equal to 2. The axiom of pairing says that if x and y are sets, then there exists a set which contains x and y as elements. This can be demonstrated very simply by moving the balls of one set into the other set. A new set is then formed, containing the original 2 sets, x, the left-hand set, and y, the right-hand set. Again, this feels very trivial, but as there is no proof of it, we must state it explicitly. So, we now know that axioms are simply accepted rules among mathematicians, statements that we can't prove but we just take to be true. Now we can go about defining the 4 axioms of a group. As I said in the beginning, I want this to feel really intuitive and natural, so I've taken away all of the formal mathematical language, so we are just left with what I hope feels like common sense. Since we know group theory is all about symmetry, let's consider the properties of symmetries. Consider all the symmetries of an equilateral triangle. There are 4 properties that are important to note. Number 1. No matter what symmetries you perform, you will always be left with an equilateral triangle, i.e., there is no symmetry that can turn the triangle into a square or anything else. This is known as closure. Number 2. There exists a do-nothing symmetry, i.e., leaving the equilateral triangle as it is still gives you an equilateral triangle, and hence it is a symmetry. This is called the identity. Number 3. There exists a way of undoing the symmetry. If you rotate a triangle 120 degrees clockwise, you can undo this by rotating the triangle 120 degrees anti-clockwise. This is called an inverse. Number 4. It doesn't matter how you combine the actions. If you had performed a rotation, followed by a reflection paired with a rotation, it is the same as if you had performed a rotation paired with a reflection, followed by a rotation. In other words, it doesn't matter how you combine the actions. This is called associativity. These are the 4 axioms of a group, and anything that satisfies these 4 rules is known as a group. Now we know what rules define a group. Let's take a look at a few examples of groups in maths. One example of a group in maths is the group of integers, or whole numbers. We can check that the 4 axioms hold for the integers. Adding an integer to an integer will always give an integer, and therefore our group is closed. A way to think about this in terms of symmetry is that you can translate the number line by an integer value, and you will still be left with the number line. Adding 0 to an integer will always leave that integer unchanged. This is the do-nothing symmetry, and as such there exists an identity element. Since the group of integers contains negative numbers, you can always undo the symmetry of translating the number line to the right, addition, by translating the number line to the left, subtraction. Therefore, there is a way of undoing each symmetry, and so there exists inverses. Finally, it doesn't matter how you put brackets around integers when you are adding them together. It won't affect the outcome of the sum. For example, in the sum 1 plus 2 plus 3, it doesn't matter whether you put brackets around the 1 and 2 or around the 2 and 3. You will get the same answer, which is 6. Therefore, the group is associative. Since the integers obey the 4 group axioms, we can say that integers do indeed form a group. More specifically, we say that integers form a group with the group operation of addition. For the more advanced viewers, we can say that this group is abelian, which simply means that the group operation is commutative. Let's take an example of a group you might see every day without even realizing: the clock. Let's check all 4 axioms. No matter what you add to the current hour, the clock will read a number between 1 and 12. This means it is closed, as there is nothing you can do, or more specifically, no symmetry you can perform, to get an element outside of the group. You can do nothing by either adding 0 or adding 12, or indeed any multiple of 12, and you will end up with the same number. Therefore, there exists an identity element. You can undo every symmetry. Suppose the clock read 12 o'clock and now reads 4 o'clock. How can we undo this? If we add 8 hours to 4, we get 12, and therefore we have undone the symmetry. Therefore, there exists inverses. Addition around a clock face is associative. It doesn't matter if we take 3 and add 2 plus 3, or 5. It is the same as if we took 3 plus 2, or 5, and then added 3. It doesn't matter how we combine these additions, we get the same answer of 8. This confirms that the set of elements on a clock, together with the action of modular addition, the mathematical term for clock addition, form a group. In particular, this is the cyclic group of order 12, which means it has 12 elements, for those who are interested in a more formal definition, as mathematicians normally are. The final example I would like to have a look at is the group of rotations of a dodecagon. Though this might feel like a random choice, you'll see where I'm going with this soon. Clearly, rotating the dodecagon will always give us a dodecagon, and so it is closed. You could rotate it by a multiple of 360 degrees, or leave it alone for the do-nothing symmetry, and therefore an identity exists. For every clockwise rotation you perform, you can perform an anti-clockwise rotation to reverse it, and therefore inverses exist. It doesn't matter how you combine the rotations, you will get the same result, and so it is associative. Now we have confirmed this is indeed a group. I want you to consider how it is related to the group formed by addition around the clock. I want you to notice that, fundamentally, there is no difference between the two groups, other than the fact I have named one the rotations of a dodecagon, and one the addition around a clock. They both behave in exactly the same way. 1/12 of a revolution for the dodecagon is exactly the same as adding 1 on the clock. But how could we formalize this notion mathematically, that these groups are more or less the same? In order to do this, I need to introduce the concept of mappings in mathematics. A mapping in maths is simply when you take a set of elements x, called the domain, to a set of elements y, called the codomain. For example, we could take the set of elements 1, 2, 3, and map them as follows to the set of elements 4, 5, 6. There are exactly 3 kinds of mappings. 1. An injective mapping is when you start with a set x and map it onto a larger set y. 2. A bijective mapping is when you start with a set x and map it onto a set y of the same size. This is known as one-to-one correspondence, as each element of x is taken to exactly one element of y. 3. A surjective mapping is when you start with a set x and map it onto a smaller set y. When we're talking about sets, you could literally assign the elements to be any value. Sets don't have the strict rules that groups have. If you simply assigned the elements of a group a random new value in any way you chose, it's very unlikely that you'd end up with a group that would obey the 4 group axioms. Because of this, there is a rule to how you can map between groups in group theory, so that you preserve the group structure. The mapping between groups that preserves the group structure is known as a homomorphism. For those of you who are interested in what this rule is, I've written it here, but it's not important that you understand it in order to be able to move on. What is important to know is that a homomorphism is a way of effectively changing the elements so that it still forms a group. Sometimes, you map a group onto a larger group, which is a kind of mapping, or more precisely, homomorphism, that we now know is called an injective mapping. Sometimes, you map a group onto a smaller group, which is a kind of mapping, or more precisely, homomorphism, that we now know is called a surjective mapping. If we take a group onto a group of the same size, we have a bijective mapping, which means we are taking each element of a group G to exactly one element of the group H. In this case, when the homomorphism of groups is bijective, we say that the two groups are isomorphic. If you think about this intuitively, an isomorphism is simply relabeling the elements of a group. If the group structure doesn't change, and nor does the size of the group, what is the difference between them other than the names you've given to the elements? The notion of an isomorphism is exactly how we say groups are more or less the same in group theory, and the examples of groups I gave earlier of the clock and the rotations of the dodecagon are indeed isomorphic. We can now formally talk about two groups being more or less the same group. I think now would be a perfect time to summarise what we've covered so far. We've discussed that a group is simply the mathematical formalisation of symmetry. We then came up with 4 rules, or more precisely 4 axioms, to define a group. We saw that integers, the clock, and the rotations of a dodecagon were examples of groups as they obeyed the 4 group axioms. After discussion of mappings and how homomorphisms allow us to map between groups while preserving group structure, we then saw that the clock group and the group of rotations of the dodecagon are isomorphic as there exists a bijective homomorphism between them. Don't worry if some of this feels a little challenging at first. These concepts are very abstract and very difficult to grasp. However, it's not vital that you understood absolutely everything to follow along with the next few topics. A few of you may be wondering what the point of all this is. Why would anyone be interested in studying group theory? I would love to answer that it is simply a beautiful thing to study, but I don't feel that would be very convincing to a lot of you. It turns out that symmetries really are quite fundamental and appear everywhere. I don't like thinking of maths as a useful subject, but it's certainly true that group theory has many real-life applications. Chemists use group theory all the time to understand the structures of crystals, which undoubtedly contain a lot of symmetry. Theoretical physicists use group theory to understand the strange symmetries of tiny particles in their complex quantum theories, which may lead us to the answer of how the universe came to be. Group theory is all around maths and often crops up when it is least expected. Perhaps most relevant today is that it is frequently used in coding and cryptography, and so it might be group theory you have to thank for keeping your devices secure. All in all, symmetry really is fundamental, and therefore group theory comes up everywhere. Even though it's very unlikely you would be able to apply it in your life, without it, many discoveries wouldn't have been made in chemistry, physics, maths, and computer science. Maybe it is important after all. As I'm a mathematician, I'd like to show you an application of group theory in the context of algebra. This area of maths is known as Galois Theory, named after Évariste Galois, who we talked about earlier. Galois Theory, very simply, describes the solutions to polynomials as a group. The fundamental theorem of Galois Theory says that if the group formed by these solutions to a polynomial have a very specific property, the polynomial can be solved. But what exactly is a polynomial, and how is group theory related to their solutions? A polynomial, which literally means many number, is simply an equation of the form an x to the n plus an minus 1 x to the n minus 1 plus on and on plus a0 equals 0. Here are a few examples of polynomials. Consider the following polynomial. The solutions are 1, minus 1, 2i, and minus 2i. Don't worry if you're not familiar with the complex numbers. The important thing is that you can appreciate the symmetry of these solutions. When I draw them in the complex plane, you can immediately see the symmetry between them, and as such, it isn't surprising that group theory crops up here. I won't go into all the detail because the intricacies of Galois theory are really quite complex, but I will mention some of the astonishing results it can prove. Namely, you can prove that polynomials of degree 5, which means x to the power of 5 is the highest power of the equation, are unsolvable by looking at the properties of the Galois group. Unfortunately, the Galois group has a definition that is really too advanced to include here. You can also prove the impossibility of trisecting an angle using a ruler and a pair of compasses, and the surprising possibility of constructing a regular 17-gon with only a ruler and a pair of compasses. Group theory is also a very important part of my favourite area of modern maths research called the Langlands Program. If we imagine a map of mathematics with all the distinct areas such as number theory, the study of discrete mathematics, and harmonic analysis, the study of functions in relation to frequency, as well as many other areas. All of these areas of maths, or continents of the map of mathematics, seem completely disconnected, but it turns out that there may be a way to move between mathematical continents by building metaphorical bridges to connect separate areas of mathematics. Edward Frenkel described the Langlands Program as a kind of grand unified theory of mathematics. I personally like to think of the Langlands Program as the symmetry of mathematics, in the sense that once the conjectures of the Langlands Program have been resolved, you should be able to translate between seemingly distinct areas of mathematics, as if the subject of mathematics itself was symmetric. Perhaps the most amazing thing I've ever come across in maths is something known as the monster group. To give some background to this, we can classify groups known as finite simple groups into 18 families, remarkably similar to the classification of elements in a periodic table. However, There are groups known as sporadic groups, which don't fit into these families. It's been proven that there are exactly 26 sporadic groups, and the largest of these is known as the monster group. It's a group that describes symmetries in 196,883 dimensions and consists of a ridiculous number of elements. After this group, every finite simple group can be classified into one of the 18 families. The mathematician John Conway was particularly fascinated with the monster group, and he did much work on it. He said, "There's never been any kind of explanation of why it's there, and it's obviously not there just by coincidence. It's got too many intriguing properties for it all to just be an accident. Even today, we can't explain why this monster group is here. It seems to be an anomaly in mathematics." Even more strangely, there was a conjecture called the monstrous moonshine conjecture, proven by Richard Borcherds, that stated there was a connection between these sporadic groups and certain results deep in number theory. The monster group is some kind of fundamental object in maths that we can't explain. It seems to just sit there, the final anomaly in group theory, as if to just taunt mathematicians. I have put some examples here on the screen of some more advanced groups for those of you who are interested, and I encourage you to prove that they do indeed satisfy the 4 group axioms. Maybe have a look around the internet to find some of the intriguing properties, because some of these interesting groups really crop up everywhere in maths. Today, we've covered a lot of ground. It's okay if you didn't understand it all, or if it was a bit overwhelming. What is important is that you at least developed an appreciation for what it is pure mathematicians like me are interested in. To give a very brief summary, here's what we covered today. Firstly, we discussed that group theory is a mathematical way of describing symmetry. We then discussed that axioms were the rules of maths that we have to define, and we went on to discuss the 4 axioms that define a group. We saw that the integers were an example of a group, as was the clock and the set of rotations of a dodecagon. We then discussed different kinds of mappings in maths, and more specifically, mappings between groups, which are called homomorphisms. We found out that the way of saying 2 groups are basically the same thing is by describing the groups as isomorphic, which means there exists a homomorphism from one group to the other, which is bijective, or 1-to-1. We saw applications of group theory in maths and other subjects, and we went on to discuss the complex field of Galois Theory. I shared how group theory is relevant to me in my study of the Langlands Program, which I consider to be the most fascinating area of maths research at the moment. Finally, and perhaps most intriguingly, was the monster group. If you were to take one thing from this lesson, I would hope it is the amazement that such a complex group exists, as the final sporadic finite simple group from the 4 simple axioms that define a group. I hope this gives you an appreciation of why pure mathematicians study this subject, because of its intriguing properties, and not because it has use in the real world. If you'd like to learn more, please consider checking out some of these resources. I highly recommend the book Algebra by Sergey Lan, which is available for free online. It covers the basic theorems of group theory in a very clear manner and goes on to discuss some very complex topics. I would also very highly recommend the series of videos called Essence of Group Theory, which can be found on YouTube under the channel name Mathemaniac. He uses a lot of animations, which makes the topic very intuitive and easy to follow. Richard Borcherds also has a YouTube channel, which you could check out. His videos are very advanced and can be very difficult to follow, but if you enjoyed the topic of group theory today, I think you'll like the topics he discusses. It's also really cool that it was him that proved the monstrous moonshine conjecture, which was quite an impressive feat for a mathematician. Perhaps my favourite of all is Grant Sanderson's popular YouTube channel, 3 Blue, 1 Brown. His videos are more or less entirely animated, and I find them a joy to watch. I think he might just be the best maths teacher in the world at the moment. Finally, I also really enjoy Aleph Zero's videos. He covers a wide range of topics, and generally, his videos aren't too advanced. I think anyone should be able to follow them. Thank you so much for watching. I hope you enjoyed covering the abstract topic of group theory today, but more generally, the concept of symmetry throughout maths, and the important role that it plays everywhere that it shows up. Until next time, goodbye.